Hello, good day, and good evening, everybody. I hope you're all doing great, and welcome to the latest episode of the Ask Abhijit show. Today is the science, physics, astronomy, etc. edition. I hope you're all doing great. Before we begin, as usual, let me greet those of you who are on the live chat. Let us see who all is there. I can see Rajat Chopra. I can see Ashish Kumar, Akash, Sujal, MS, SB, Arinthkir, Ashish Vishwakarma, Pradyumna, Janvi, Bibekananda Panda, Tejo Meg, hello. Toji, Ralla Avinash, Sarthak Singh, Om Bekerikar, hello. Animish, hello. Namaste. Dungar Singh Chauhan, hello. Siddhant Singh Chauhan, hello. Malik Sayed, hello. Sigma, good evening. Geopolitical Dubai, hello. Raghuvir, Rakshasi Raj, Aditya Thakur, Pavan Kumar Singh Bais, Noma Droni, Amar Chaudhary, Sachin Giri, Harish, Akshay Shinde, Vishaka Bila, Bitupan, Bora, Sagar, Dog, Pranay Kumar, Akshay Shinde, Rakshasi, etc., Vikrant, Animesh, Prabhat Arya, Ayush, Threadripper, One Unkar, Bitupan, AJ, Rahul, Meditation and Relaxation, Ashish, Shivanshu, Samarth, Pandey, hello, Shriram Mohan, and lots of other people. Dungar Singh Chauhan says Rajasthan may meet up karo. Okay, let's try and do that. Okay, so we're gonna take a bunch of questions as always, but before that, I have an announcement. So those of you who are planning to attend tomorrow's live stream, it is unfortunately being moved to Monday. I have been invited to Prime Minister Modi's inauguration tomorrow, so I'm gonna have to attend that, obviously. So tomorrow's live stream will happen on Monday, 9 p.m. on Monday, not tomorrow. So yeah, one announcement. So who else? Let me briefly greet some more people. Apurva, Nikhil, APS Talks, Ajinkya, Shri Harsh, Gautam, Animish, Swapnil Mishra, hello. Disciples of Mind, Anshul, Somnath, Chittij, Sami Point, Hitman, Spy, Shashi, Super Saiyan Sins, and everybody else. All right. Okay, enough greeting. Greetings to everyone. Now let's take some questions. So I'm going to take a number of questions, maybe 10, 15 questions I will take from the comments. And then at the end, I will take as many as possible from the live chat. So that's going to be at the end in the second half of today's session. So I'm going to keep it maybe 40%, 60% from the comments and 40% from the live chat, that sort of thing. That's what I shall do today. Okay, what are the questions that we have? Okay, we begin with Swapnil Mishra's question. The question is, what was the great unconformity time period during which a huge chunk of the Earth's paleontological timeline disappeared? Okay, I hope I haven't taken this question before, but anyway, let's take it. So, this is a question about geology, about natural history, like the hashtag says, the hashtag over here, natural history. It's a geological question. So, the Earth, as we know, has sedimentation, and sediments naturally get deposited on the crust of the earth and the bottom of the oceans through natural processes, and this typically takes millions of years. So if we and over time, because of geological processes, these sediments and these formations, there is upheaval, geological upheaval, and these eventually break out through the surface of the earth. And lots of mountains, if you go to the Himalayas, you will see lots of sedimentary layers, layer upon layer upon layer. In each layer typically is it represents a time period of tens of thousands of years, sometimes hundreds of thousands of years. And a 1 foot, 2 foot thick layer of multiple sediments could be several million years. So that's how it happens. Now, and we can date the sediments, that this layer of sediment, these particular sediments, they date from what time period and so on. There are various means and ways and means of doing that. So we can determine at what level which sediment existed, was formed. So if you want to see what sediments look like, let me put that on the screen so that those of you who are not aware will get an understanding. Okay, so earth sediments. So what do sediments look like? So see, you will see rocks in mountains and hills that have these layers. So each of these layers generally represents a sediment that is thousands, maybe tens of thousands, maybe millions of years old. And you will see this all over the place. I'm sure everybody is familiar with such sediments, and you can see that there are people standing on top of this formation, and below that there are sediments that would go back hundreds of thousands of millions, maybe billions of years at times. And you can see that each sediment, every stratum of sediment has different characteristics, different colors, and so on. So this is a snapshot into the deep history of the planet itself. And you will often find fossils within sediments. Some sediments have shocked quartz and iridium, which is the indicator of a significantly large impact event, like the last impact event extinction, the Chicxulub event that happened about 66 million years ago. And you discover, if you go back that at that particular point in time in sediments, you will discover iridium, and you will discover shocked quartz, and you will discover many other things like spherules and all that. So that tells you that something drastic happened at that time. So that is what sediments are. Now, what is the great unconformity time period? It is essentially an absence of sediments from a certain period in our planet's history. So if you go back, if you go to places like the Grand Canyon in North America, which is currently part of the US, and so on, you will find all these exposed sediments on the surfaces of the hills and various formations, and you will find that certain time periods are missing. There's a significant missing time period between half a billion to 1.2 billion years, that sort of time period. And for that time period, which begins, if we start going backwards from today, it starts about 530, 540 million years before today, and it goes all the way back to maybe a billion and a half years before today. So that gap of time is missing in the sediments, and you find this in various parts of the planet, not just at the Grand Canyon. And that is the great unconformity. Missing evidence. I mean, missing sediments of the Earth's natural history. So that's the great unconformity. And the question is, why is this time period missing from all these sediments? Why don't we have layers pertaining to that time period? And we don't quite have answers. We don't quite have the answer to why is that time period missing from the sedimentary history of the planet. It's a mystery. And there are possible solutions that have been proposed. Maybe there was a lot of erosion or whatever in that time period, which is why the sediments could not form and they could not settle down in the bottoms of the oceans. A lot of churn of some kind. So we don't quite have the answers right now, but that is a big mystery. So there's mysteries not just in theoretical physics when it comes to dark matter, dark energy, all that stuff, and much more. There's mysteries when it comes to the history of our own planet itself. Lots of mysteries when it comes to Earth's natural history, right? So this is one of those mysteries, and there are many more histories. The origin of life is a big mystery, but the great unconformity, that is a missing. It's a gap in our in the hard history of the planet. The sediment, those layers are missing, and we don't quite know why they are missing. So yeah, that's what it is. So that's the question we begin with. What's the next question? Geopolitical Dubey asks a question about volcanoes. Okay, what if all trash, all plastic waste, etc., was thrown into volcanoes? Let's say we start throwing all the trash, all the plastic waste, everything into volcanoes. What will happen? Because trash is a problem, garbage and waste is a problem. We know the oceans are getting choked with plastic. There are gigantic, you know, trash repositories in the oceans, entire island sized and almost small continent sized uh, regions in the Pacific Ocean, where there's just garbage everywhere. It all just it all accumulates because of the currents of the ocean and so on. So there is a huge problem, this plastic and various other garbage, various other trash that we human beings produce. What do we do with it? Shall we dump it into the volcanoes? Now, in case you all don't know what a volcano looks like, let me put that on the screen. One second, give me a second. So, what is a volcano? Is the question, right? So, volcano is this thing here. That's volcano. So, volcano is a mountain. It's essentially a mountain that is a portal into the deep netherworld beneath the surface of the planet, and the magma layer comes into contact with the atmosphere and it spews out lava, and the lava accumulates in the form of these conical mountains. And sometimes you have dormant or extinct volcanoes which leave behind lakes in this manner, and so on. This is a volcano. So what if we take all the trash, all the plastic waste, all of that which we don't need, and maybe which we are not able to recycle? What if we just dump it into volcanoes? What happens? And I would say it's a good question. It's a legitimate question. What happens? Why not do this? So here's what happens. Let's say you take plastic. Now, plastic is a byproduct of hydrocarbons, right? Uh, to make plastic, how do we manufacture plastic? It is something that is manufactured from processing hydrocarbons, essentially oil, petroleum oil. So it's a petroleum byproduct. There are certain processes uh, that we make the petroleum undergo, and plastic is a byproduct of that. So plastic essentially is a carbon compound, a hydrocarbon most likely. I'm not sure what the chemical structure, the chemical composition is, but there's carbon in there. And plastic is non-biodegradable. So let's say you take plastic and you dump it. Let's say you take 100 tons of plastic and you dump it into a gigantic volcano. There are such volcanoes that you can do that in. What happens? The volcanoes, the lava is at an extremely high temperature. It is molten rock. So it's going to be hundreds of degrees Celsius, maybe more. Okay. So you dump plastic in there, the plastic will immediately ignite. It will catch fire. Plastic is reasonably less dense, significantly less dense than molten rock. So plastic will float on the lava and it will melt and it will burn. So when plastic burns, it's going to emit all kinds of carbon soot, carbon dioxide, maybe carbon monoxide, and various other chemicals. And they're going to go out into the atmosphere. So that's not what you want. You want to reduce the carbon emissions, but by dumping plastic into a volcano, you're going to ignite the plastic. It's going to burn and bubble and steam, and all of these gases that are output from that will go into the atmosphere. And it's mainly carbon products, carbon based gases like carbon dioxide and whatever else is part of the plastic that you're dumping in there. So that's not a good idea. The plastic, all the trash will not simply sink below the surface, it will all burn. So instead of doing that, you may just incinerate all this garbage. It's going to have the same effect as incinerating garbage. And incinerating garbage is a very bad idea. We know that. I mean, there are various parts of the world where instead of processing or recycling garbage, governments just incinerate the garbage, essentially burn it. And what that does, it creates this horrible smog, this haze in the atmosphere. There are, I'm sure there are Indian cities when you're landing, you don't see the city, you just see a layer of haze. Well, that's what it creates. So, dumping plastic waste and other kinds of waste inside volcanoes is going to cause that effect. It's going to create that problem. It's the same thing as incinerating garbage, and that is not an environment friendly exercise or activity. So that's why it's not a good idea. And obviously, volcanoes are unstable. And how do you take the hundreds of tons of garbage all the way to the mouth of a volcano? What if it crumbles and you also go in there? You don't want to do that. So, overall, it's not very practical. And even if it were to be practical, it is not a very good idea because it's going to release tremendous amounts of carbon into the atmosphere and contribute further to the climate change, the human mediated climate change, which is in addition to the natural climate change, which has always been happening. All right. Okay. Vishal Kumar says, what is fire? How is it produced? And why is it produced? Fire. I think we all know what fire looks like. I don't think I have to Google and put images of fire, but let's just do it just in case. Shall we? Let's put images of fire on the screen. Fire. So this is what fire is, right? This is what fire is. So flames. We are all familiar with flames, matchsticks, gas that people use, gas pipelines, and you use that for cooking purposes and so on. And flames come in various colors depending on the temperature and what you're burning and so on and so forth. That is fire. Now, this is a very good question, actually. Vishal Kumar asks, what is fire? I mean, that's a very basic question, very fundamental question, and I'm sure all kids have this question. That this thing that we see, what is it? What is fire? I remember when I was a kid, I had a cat. I've always had cats as a kid. So I had this cat, and he was a kitten. So he was like an adolescent. From a human perspective, he would have been a 13 or 14-year-old. So this cat, when I was a kid, there used to be power failures in India. So there was a power failure, and there was a candle that we had put up on the floor. So this cat, he sees this flame, and he's curious. Kids are curious, and he's a kitten, so he's curious. So he goes all the way to the flame. He puts his nose in the flame and sniffs it, and then he jumps 6 feet high in the air. And I promise you, he would have never done that again. That's how he learned. So even cats are curious about what is this. Let me go and sniff it. Yeah. So the question is, what is fire? And that's a very good question. So fire is not just a chemical reaction, it's also a physical reaction. Well, it's an oxidation process, a very rapid and exothermic process. Which So what is oxidation? It is a chemical reaction between something, which is the fuel, and oxygen, which is part of the atmosphere. So if you create a vacuum, if you evacuate a box and you remove all the air from it, you can't have a flame in there. You can't burn anything there, no matter what you do. Okay. So fire is a rapid oxidation process, which means it's an exothermic chemical reaction. Exothermic means it gives off light and heat. Okay. So the reaction products are what is produced by this reaction is light, heat, and other reaction produced. It's an exothermic chemical reaction, which is also called combustion. So what's the chemistry of fire? So first of all, what are the components? What goes into creating fire? Let's break it down. First of all, we have fuel, or what is called reactants. So wood, paper, uh, gasoline, petroleum, whatever you want to call it, methane, hydrogen gas. Okay, this is the reactant. This is the substance that burns or gets oxidized. That is number one. And secondly, you have an oxidizer, which is typically oxygen from the air, but you can also use, let's say, in rocket fuel, something like hydrogen peroxide or something like that. So that can also work as an oxidizer. But from our perspective, we'll just talk about the oxygen in the air. So you have the reactants, which are the fuel and the oxygen, and then you have products. So what comes out of the fire? So we have carbon dioxide. Let's say you're burning wood. The typical products of this chemical reaction are going to be carbon dioxide, water also, and heat and light, because you can sense the heat and you can see the light. Okay. So so that's the chemical reaction. You're going to have fuel plus oxygen, and you're going to induce this chemical reaction by applying heat, by giving it a source of heat, and it gives off carbon dioxide, water, and heat and light. Okay. Now, what are the stages of this reaction, this combustion reaction? First, you have ignition. So you have seen ISRO in SpaceX videos, and 9 8 all the way to 0, lift off normal. Love the accent, I just love it. We own that. So you will see that when you're about to reach 0, the fuel is being emitted from the rocket, whether it's a PSLV or LMV, whichever, and suddenly there's a spark, and then the fuel ignites, and whoosh, the flame comes out, and then it propels the rocket upwards, right? So that is ignition. So the process of fire, we're breaking it down here. Okay. So the process begins when the fuel reaches what is called its ignition temperature. Every fuel has a different ignition temperature. Plastic will have a different ignition temperature. Wood, for various kinds of wood, the ignition temperature will be different. For paper, it will be different. For whatever else, it will be different. For various gases, it will be different, and so on. So once the fuel reaches the ignition temperature, that's when ignition happens. And what happens in ignition? There are chemical bonds within the fuel molecules, and these will break because of the ignition temperature, and then they will start reacting with oxygen. That is ignition. The spark has been lit, and the fire it just begins. Then the flame will propagate. So as the reaction, this ignition, as this oxidation reaction progresses, the heat generated by the combustion will sustain the reaction. So now you don't need any more outside, uh, you don't need any heat from outside anymore. Now that the flame is on, it's gonna keep on propagating and sustaining. It's kind of a chain reaction. So the combustion will continue to propagate and continue. So it's a chain reaction. Combustion is a chain reaction, which means that the heat generated by the reaction provides enough energy to sustain the reaction as long as fuel and oxidizer are both present. Okay, and then we can talk about the physics of the fire. So there are various kinds of heat transfer, which is combustion, and convection, which means the transfer of heat by movement of fluids, typically gases. Conduction means direct contact, which means, two substances in contact with each other. There is radiation as well, transfer of heat in the form of electromagnetic waves. Then there is the emission of light, because we see that flame is, it produces light. So there are two ways in which flame produces light. I mean, we can think of two ways. One is black body radiation. The heated gases, they emit light due to a process called black body radiation, in which objects emit lights of various frequencies or colors based on their temperature. And then you also have excitation of molecules, which means the electrons in the atoms of the burning material get excited to a higher energy state, higher energy level, and then they come down to the ground state by releasing photons of light, which is light itself, of various colors. So that is fire. I think I've really broken it down. And so you need a heat source, you need the fuel will react with oxygen, it decomposes, it breaks down into various other compounds, various things. You can have soot that comes out of it. We can have soot, you can have volatile compounds which again react with oxygen, and so on. So that is what fire is, and fire can come in different colors depending on what you're burning. if you burn if you burn sodium, it produces fire of, I mean, you have spectroscopy, in which you have white light can be broken down into various spectra. We look at the spectra of stars, and you can burn the same things to produce the same colors that you have in the spectra of stars. So if you burn sodium, you burn magnesium, etc., you will have lights of different colors depending on which atom it is and what are the energy levels between which the electrons are going up and coming down, and so on. So that is what fire is. You can do a week long seminar on fire. Actually, that's how complicated and interesting this very straightforward mundane process is. It's a complicated interplay of chemistry as well as physics, chemical reactions and physical processes, oxidation of fuel, you need an oxidizer, there's light emission through exothermic reactions, and so on. That is fire. Very interesting question. And I wish that when kids ask these questions, they are not told to shut up, and somebody actually gives an answer to this question. Anyway, good question. Okay, geopolitical Dubey says, how do windmills work, and how strong of an energy can a windmill generate? Windmills. So a windmill. Okay, let's go to Google and see what a windmill looks like. Okay, we'll go to blank Google and say windmill. Windmill. We go to image. Nope. Nope. Google search. Images. A windmill. So this is a windmill. I'm sure we've all seen them. We've had historically we had these smaller windmills. This is something that you would see in Don Quixote, Don Quixote, and Sancho Panza. That story. That's what ancient European windmills would look like. This sort of thing. And then you have modern windmills that you will see all across the hills and everything. If you are in India, there are lots of hills and the Western Ghats and wherever else that you will see mountains and hills that have hundreds of windmills placed atop them on the slopes, wherever it's easy to catch wind. So this is what a windmill looks like. Okay. So it's essentially an object. It's a machine, very simple machine. You have a stand. As you can see, there's a stand on which there are these turbine blades, usually three blades, and the blades are configured in such a manner that they will catch the wind, and the wind will make the entire contraption go round. Okay, so it's gonna move in this circular fashion. So that's what it looks like. Now, how does a windmill work? So once again, let's go to the image. A windmill, let's say diagram, right? diagram. So, what are the constituent parts of a windmill? Okay, there are various names. So, we have the blades, the turbine blades or rotor blades, let's call them. Okay, and the wind makes these blades turn. Now, there is a shaft which connects the blades, the blade apparatus to a gearbox, and the gearbox will 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 then turn uh, this system, and there is a generator with copper coils or whatever. And essentially what it does is it produces electricity through electromagnetic induction. That's what it does. So you will learn in electromagnetism that moving magnets, when magnets move, they generate an electric current, and when electricity moves, it also generates a magnetic field. Electromagnetism is all about electric and magnetic fields. So through electric induction, they this machine generates electricity. And it depends how much energy, how much electricity, not energy, electricity, a windmill generates depends on the size. It depends on the size of the turbine, on the size of the entire, not the turbine, the blades. It also depends on the size of the entire windmill. It also depends on the weather conditions, the wind conditions, and all that, and so on. So generally, when it comes to a windmill, once the speed of the blades of the turbine, it reaches 5 to 10 kilometers per hour, that's generally when it starts generating electricity. And I think if it reaches 20, 25 or beyond, it's going to shut off automatically just for safety. And so a windmill that is used, let's say privately in a home, or in a, yeah, let's say a private windmill, a private wind turbine will generate electricity in the kilowatt hour range. But commercial and industrial wind turbines, which are like the giant ones that we see from far away from aircraft and all, those will generate electricity in the megawatt hour range. And there is an energy capacity also for each wind turbine, which is a dimensionless number. It's a fraction, zero point 0.1 to 1.0. 1.0 is not attainable, so it's generally 0.25 to 0.5, 0.6, and that tells you how efficient the windmill is. So that's what it is. It's a very complicated engineering subject, but the fundamental, basic, simple principle is that it generates electricity through a phenomenon called electromagnetic induction. That's what it is. So it's essentially free energy. Wind energy comes from the sun. Okay, you have the planet, half of it is dark, half of it is in sunlight at any given point in time. So the half of the planet which is experiencing sunlight is going to be warmer, and the half of the planet which is currently dark, nighttime, is going to be cooler. So you're going to have a warm side and a cool side of the planet. And when you have hot and cold, then there's going to be currents of air, because cooler air is heavier, hotter air is lighter. So cooler air will flow towards the hotter side, and so on. So there are these currents of air that are generated, and that's how wind is generated in the atmosphere of the earth. And there are low pressure areas, high pressure areas, and so much. It's very complicated. Trillions of parameters, I would imagine. That's why you need supercomputers to predict weather patterns. So that's how wind is generated, and the wind is generated because of the heat that's coming from the sun. So it's free energy. So it's good to have to harness that, because that is great. You don't have to burn fossil fuels to generate that energy. Of course, it is not very reliable. Wind can stop and start, and it's not always reliable, but it's good to have this. So that's what windmills are, and that's how it works. Okay, Aditi says this question is important to me. Please tell me about palm oil. I have heard of it being injurious to human health, if not for human consumption. What good can palm oil serve? Can it act as a fuel in manufacturing, or for industrial purposes, or farm animal raising sector? Also, what is its scope, especially related to India? I'll be grateful. Okay, thank you. So, palm oil is the question. Now, what do we do about that? So, palm oil is, there is a tree, a plant called the palm tree, and palm oil is generated from the fruits. It is extracted from the fruits. So let's go and see what the palm tree looks like. Palm oil tree. Okay, let me put that on the screen. If it Yeah, there we have it. So that's what the palm tree or palm plant looks like. This is the fruit it produces. It's got a very nice aroma, and it's very rich in oil. So that's what the fruit is like. And so this is from what you generally extract, palm oil. Now the question is how healthy or not is palm oil. And I am not exactly an expert, so let us go to let's search for palm oil dangers, and we'll just review maybe an article, a research article, research paper. And let's go to this one here. So what's it say? uh, so the dominance of, see, palm oil is used in processed foods. Now, when it comes to low income nations, you typically will not see much prevalence of processed or hyper processed foods. But when a nation is transitioning from a low income status to a middle income status, you're going to see an increasing prevalence of hyper processed foods, like, the packets of chips and junk food and fast food and all that. And these typically use palm oil. And India, for example, is one of the major importers, I believe, of palm oil. Now, okay, so palm oil is one of the world's most commonly used vegetable oils. It's used in snacks and cosmetics. It's present in about half of frequently used food and consumer products, and so on and so forth. So, a meta analysis of increased palm oil consumption in 23 countries found a significant relationship with higher mortality from ischemic heart disease, which is coronary heart disease. Another systematic review found that palm oil consumption increased blood levels of atherogenic, low density lipoprotein cholesterol. Uh, and the WHO has described that the evidence linking saturated fat consumption with increased risk of cardiovascular disease is convincing. And there's a lot more over here. So clearly, it is something that is hazardous. Okay, palm oil is not the kind of oil you want to consume. And it is also said that they also said that coconut oil isn't that healthy, but we have been in India using coconut oil for thousands of years, and we don't really. I'm not sure if any studies have been done studying the correlation between coconut oil consumption and any health issues. I am not aware of any, but palm oil definitely is a risk factor. So I would say that palm oil is hazardous to health. It is connected with an increased prevalence of coronary heart disease and bad cholesterol, an increase in the bad cholesterol in your blood. So it should be avoided. What that means is that avoid eating hyper processed foods, all those fried things that come in packages, in packets, whether it is chips or whatever, curly fries or whatever it is, all that, and other things as well. Maybe canned products, maybe maybe what do you call it? Quick noodles, 2-minute noodles or whatever it is, all that stuff. You should read the ingredients, and sometimes it may not even be listed. So ideally, what you want to do is just eat natural foods which you cook yourself, nothing processed. So that's the deal about palm oil. That's what I can say. Can it act as a fuel in manufacturing or for industrial purposes? I'm sure you can use it for that. I'm sure it can be used. So the thing is, India is a major importer of palm oil. I think India imports significant quantities of palm oil from Malaysia as well as Indonesia. And recently there was some diplomatic spat between India and Malaysia, and we stopped importing it from Malaysia, and that was not good for Malaysia. And they kind of tried to convince India to start importing again from them. So India is a major importer of palm oil, which means a significant amount of the hyper processed foods that we find in India will have palm oil in them. And that is not good for your health. So I would say limit your consumption of all this junk food, fast food, hyper processed food. Eat healthy, eat clean, eat food that is natural. The best policy in life, I would say, is to eat whatever your ancestors were eating 1,000 years ago. If they were eating it then, you can eat it today. And yeah, so that's what I would say. That's a great heuristic for what is healthy and what's not. Okay, next question is by Sri Rag Nair. Okay, will you talk about photonic integrated circuits? This is an emerging technology and the opportunities are immense. Photonic integrated circuits. Okay, so what are photonic circuits? Photonic circuits are circuits that use light. Okay, so we know about computer chips, microchips, CPUs, all that. These are microprocessors and various logic gates and all that are etched on silicon wafers, and it works through electrical impulses, right? You have semiconductors that open and close gates and all that. So that's what you typically have in computing. Though that's the kind of circuits you have on silicon wafers. Photonic circuits or photonic integrated circuits, like Shri Nair is saying, these are devices that use light. These devices use photons instead of electrons. So instead of using electrical signals, you're using light impulses, light signals, photons, to perform the same functions, various functions like data transmission, signal processing, computation, all that. So that's what a photonic circuit is. So it is the same thing. It is the analog of electronic integrated circuits, but they operate using light. That's what it is. So that's what it is. Now, how do they work? What are the building blocks? What are the fundamental building blocks of photonic circuits? When it comes to electronic circuits, you have silicon and you have semiconducting material that acts as logic gates, and you have electricity that passes through this, and it performs various operations, logic gates, and or not, XOR, and so on and so forth. The same thing can be done through photonic circuits. Now, what are the building blocks? You will have, first of all, waveguides. Waveguides are like, you can think of them as pipes through which light passes. So they confine light and they guide light through specific paths, similar to how wires guide electrical signals. So that's waveguides. They're typically made from materials with high refractive indices. There's something in optics called the refractive index. So you use waveguides. Are made from materials with high refractive indices, such as silicon or whatever else. Then you have splitters or couplers. So these devices, they will split or combine light signals from different waveguides. You take multiple waveguides and you bring them together, the signals. So this is used for distributing light signals across various paths of the circuits. Then you have modulators, you have detectors, you have resonators, and lasers, and so on. So all of this is what goes into creating a photonic integrated circuit. There are certain advantages that photonic circuits have. First of all, they are faster than your standard electrical circuits, because light travels faster than electrical signals. So photonic integrated circuits will operate at higher speeds. So they are better. They are actually ideal for high speed data transmission and processing. And we already know that we have fiber optics which make use of the same thing. And fiber optics have excellent fidelity and all that. Uh, Now, bandwidth, when it comes to bandwidth, photonic circuits can handle a much higher range of frequencies or wavelengths compared to electronic circuits. So you will have much more data that goes through your circuit. The data throughput is much better than when it comes to electrical circuits. There is heating. When it comes to photonic circuits, these circuits, they generate much less heat compared to electronic circuits, and so on. When it comes to electric circuits, there is there is a lot of the possibility of electronic interference. When you have photonic circuits, they are immune to electromagnetic interference. For example, you need Faraday cages and all that. In the case of photonic circuits, you won't have that, and so on. And there are lots of applications of photonic circuits. For example, telecommunications, you can use them in data centers, you can use them for computing itself. Quantum computing is a very major application of photonic circuits and all that. So that's what you have it. That's what you have. Now there are challenges. This is a new technology. How to integrate photonic circuits with existing computational systems, computer systems, electronic systems. How do you do that? That's challenging. So you have to take a photonic signal, a light signal, and convert it into an electric signal when you are interfacing a photonic based device with an electronic device. Manufacturing is difficult. There is a lot of complexity and you need a lot of precision. These are all engineering challenges which will eventually be overcome. That's where we are. And then there will be limitations of various materials. It depends on the kind of materials you're using and how good those materials are. So finding materials that are efficient as well as compatible with existing semiconductor manufacturing processes is a challenge, and so on and so forth. So it's an emerging technology, and it's going to eventually become a big deal, and we are already transitioning towards that, especially when it comes to things like quantum computing, etc. So that is what photonic integrated circuits are. It is something that can work actually better than the electronic microprocessors and electronic circuits that we have in use today in all our devices, whether it's a phone, a laptop, or whatever. It is something that will eventually be a much better, much more robust, much more powerful technology. There'll be very less heating. It'll be much faster. So it makes sense to invest in the development of this technology. And like you say, the opportunities are immense. Okay, Ritik Pawar says, if AI becomes conscious and takes over power, do humans have any chance of regaining control through military action? What if the AI takes over power only in the US and not other parts of the world? Will be fun. Will be fun. Okay, let's say AI becomes conscious, and like you say, Ritik, it takes over power. It takes control of power. It comes to power somehow. So, what does it mean when we say that AI has, first of all, conscious? Okay, let's say it becomes conscious. The moment of the singularity, let's say it becomes conscious and it takes power, which means that the government is no longer in power. It takes power. That's what you mean, essentially. Because in any country, let's say the US, who is in power? It's the government that's in power. What do you mean by power? What do you mean by being in power? It means you control everything. You control the financial system, you control the military, you control the police force, you control the administrative machinery, you control Congress, you control the lower house, the House of Representatives, you control everything. Okay, so it's a command and control structure. You give orders and people execute those orders. So everything, electricity, power generation, all of that. Now, how does AI take control of the police force? How does it do that? Can it really do that? It can't. In today's world, it can't. How does AI take control of the military? You have the entire military, hundreds of thousands of soldiers, marines and air force and navy and the infantry and whatnot, and the vehicles that drive, the planes that fly, the ships and boats and submarines they operate. How does AI take over that? In today's world, it can't. If for AI to take control of everything and to really take power, it needs to be able to control every aspect of whatever we just spoke about. Every aspect of the policing process in a country. Okay, the command and control structure of the police of every state, every county, every city, every town, every village, the entire military structure has to be controlled by the AI. So essentially, this will only happen, my friends, when the police force is entirely robotic and the military is entirely robotic. As long as humans perform the major tasks and roles, AI can't take over. Understand that. AI can't take over unless everything is fully robotic and can be controlled by AI itself remotely. So, so right now, AI is not in a position. It may perhaps take over the stock markets, possibly. It may take over telecommunications, which means the president can no longer give orders to the armed forces, to whatever, and so on. There may be a disruption of telecommunications. That's what AI can do today if it takes over, if it's malicious. Uh, it could possibly perhaps launch nukes, but I don't think that works because the president's orders are involved and there's a whole sequence of events that needs to happen for the president to be able to give his assent, to press the big red button. So there is a human element involved in this for sure, and the AI won't be able to override that at this point in time. So AI can take over an entire country only when everything is entirely automated, everything is electronic, and everything is robotic. Which means all your soldiers, all your fighter planes, all your drones, all your ships, all your submarines, everything needs to be robotic, and all your police also have to be robotic. Robotic police dogs, robotic everything. Only then can a AI really take control. Right now, we're not there yet. Okay, but let's say hypothetically, 20 years down the line, everything is robotic and AI takes control. Then can you take military action? Well, in that situation, your military is robotic and it's under the control of the AI. So how do you take military action? Right? But let's say today AI tries to take over control. It takes over the stock market, let's say. It takes over the electrical grid, the control of the electrical grid. It takes over telecommunications. It takes over the control of the internet and all. You can still override that manually by sending engineers and whatever else and humans to physically cut off the AI or whatever. As long as AI doesn't have control of any offensive weapons or capabilities, AI is essentially helpless. So right now we are not there. That not yet that not yet there. So in the future, so that's how an AI can take over. So that tells us what we should not do, what steps and measures we can take right now so that AI can never take over. Which means don't make the entire military robotic. Don't make the entire police force robotic. Not even a small percentage should be robotic. Okay, you can have autonomous drones, autonomous submarines to an extent. Maybe the Americans want to have and the Chinese want to have these robotic dogs with machine guns attached to them. Well, you do too much of that, then AI can take over. Yeah. so so that's what needs to happen. It won't be fun. It'll be a disaster. Actually, it'll be a disaster beyond imagination if AI takes over robotic military and robotic police force. It is going to be disastrous. That's the Terminator scenario. That is exactly the Terminator scenario. And of course, in the Terminator scenario, AI has control of the nukes, and it causes a world war by launching nukes at the USSR or Russia. So yeah, you don't want to give AI decision making capabilities and nuclear launch capabilities, and you don't want a robotic military and a robotic police force. You take these precautions. AI can't take over beyond maybe the stock market or whatever, and you can always override that unless the AI is decentralized and you don't. In which case there are other complications. But yeah, overall that. All right. Okay, Shivam Kumar says, "What is space? What is space?" A good question. Once again, it's like the question, "What is fire? What is space?" So there are different ways of looking at what space is. The simplest answer is that space is the area, or it's that part of the universe that lies between interstellar objects like star systems, solar systems, between planets, and so on. It's the void between astrophysical objects. That is space. And as we know, it is mostly a vacuum. It's a near vacuum, not entirely a vacuum, because you have photons, light photons in the void of interstellar space. You have that. You also have a very thin diffuse you have some you have protons, you have electrons, you have hydrogen ions essentially, which kind of permeate interstellar the interstellar void or space at a very 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 low density, which is why interstellar space is a near perfect vacuum, almost perfect. uh it has gravitational fields, space. Okay, the large scale structure of the universe is mediated. It is governed. It is yeah, it is governed by the gravitational fields at the very largest scales. So you have gravitational fields, and then you have dark matter, most likely, and you have dark energy. All of this is within space. And then space, yeah. So when we speak about dark energy, space is something that is expanding. It's expanding. And maybe so dark energy is possibly something, some phenomenon, some fluid, some force, whatever it is that is responsible for the expansion, the accelerating expansion of space, and not just space time. So, from the general relativity perspective, space is part of a four-dimensional fabric called space-time. Space itself has three dimensions. That's the dimensionality of space. Dr. Subhash Kak has a theory, new theory, very good theory, in which space could be e-dimensional. E is look, check it out. What is E? The number E. It could be e-dimensional, which is less than three, which is very, very interesting. Very, very. It's a fractal number. From the perspective of quantum field theory, space is not empty. It is teeming with quantum fields, and particle antiparticle pairs are constantly popping into existence and annihilating themselves spontaneously. So it is teeming with this quantum quantum fluctuations. So all of that is space. Space has a temperature. Space is awash in the whatever is left of the afterglow of the Big Bang, which we call the cosmic microwave background radiation. So space is awash in that, and the temperature of space is about minus 270 Celsius, which is just about roughly maybe minus 271. So just a little bit above absolute zero. And the temperature of space is the temperature of the cosmic microwave background radiation, which is a very, very redshifted light, the first light that was formed in the universe, the which we could call the afterglow of the Big Bang. So all of this is space. You can define it in so many different ways. But the simplest definition from a non physicist's perspective, from a completely layperson's perspective, is that space is the void between astrophysical objects. You are at one astrophysical object, let's say you are at a star or a planet, and you want to go to another planet or another star system. What comes in between this void, that is space. All right? All right. Okay, Malik Sayed says, we know that light requires about 8 minutes and 20 seconds to come to the earth from the sun. Yes, that's, yeah, 300,000 kilometers per second, meters per second. Yeah. Uh, what is the speed of light? How can I forget? Is it 300,000 kilometers per second, or is it meters per second? Let's quickly um, let's check it out. Let's go to speed of light. I think, yeah, speed of light. Yeah, meters per second. About 300,000 meters per second is the speed of light. So, once again, the question is, we know that light takes this much time, about 8 minutes, 20 seconds, to travel from the sun to the earth. Now, what does it mean? If the sun hypothetically disappears, then we will not see the sun after 8 minutes or 20 seconds. My question is, will the earth continue orbiting the sun until that 8 minutes and 20 seconds is elapsed, or will the impact of the disappearance of the sun be instantaneous? If it's instantaneous, then we can say there is nothing faster than the light. So can we use it for human travel in the future? Okay. Oh, good question. Okay, so let's put the solar system on the screen. Let us put that on the screen. Okay. Uh, 1 second. Let's go to this. And solar system. And so this is what the solar system looks like. Let's take this as an example. So we have the sun. Okay, this is a very, let's say, let's take this toy image as an example. So you have the sun at the center, then you have the planets around it: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and they have omitted Pluto, but whatever. Okay, so we have these objects in orbit around the sun. Now let us do a thought experiment. It's called a thought experiment or a Gedanken experiment. Let's say we make the sun disappear like that. So all of a sudden, there is no sun at the center of the solar system. What happens now? What happens? So there are two perspectives, two ways of looking at this. So keep this image of the solar system in your mind. The sun with the planets going around it. It's a very rough image, but you get it. So we make the sun magically disappear in our thought experiment. So when the sun disappears, what happens? There are two perspectives, like I said. One is the Newtonian perspective, one is the Einsteinian or general relativistic perspective. From the Newtonian perspective, gravity is an action at a distance force. Okay? So from the Newtonian perspective, the moment the sun disappears, all the planets that are going in circles suddenly will be in free fall. They'll just fly off in all directions instantaneously. Instantaneously, they'll all fly off. Because of the sun's gravitational pull, they are being forced to travel in circles or ellipses. Okay, so let's say circular paths just to make it simple. They're traveling in simple circles because they're being pulled by the gravitational force of the sun. If the sun disappears, they will instantly fly off in straight lines. Okay, that's what happens from the Newtonian perspective. Now, okay, and that's what happens from the Newtonian perspective. Now, what about the general relativistic perspective? From the perspective of general relativity, gravity is not an action at a distance magical force. What we perceive as the force of gravity is actually the curvature of space time, which is produced by the presence of mass. So, in GR, in general relativity, the universe is a four-dimensional stage, space time, space and time together, four-dimensional structure, and the presence of mass curves space time, and the curvature of space time tells mass how to move. So because this sun, this massive object, is present over there, that's why the space time is curved by it, and this curvature of the space time tells all the planets to move in circular or elliptical orbits. Now, in general relativity, there's a speed limit, which is the speed of light. Nothing travels faster than the speed of light. So if the sun magically disappears, then so its light rays are traveling to the earth. Now it suddenly disappears, so there's no more light coming in. But those light rays which were already emitted, they will keep on traveling towards the earth. And for the next 8 minutes and 20 seconds, we will keep on seeing the sun, even though it's actually disappeared already. So we will not come to know for 8 minutes and 20 seconds that the sun has actually disappeared. And it's only then that the gravitational effects will become apparent. So for 8 minutes, 20 seconds, the Earth will continue in its orbit and it will continue seeing sunlight and seeing the sun as if it's there. It's only after 8 minutes, 20 seconds that you will suddenly perceive darkness, that the sun has disappeared. And then Earth and the other planets will fly off in different directions. That's what actually happens. So the correct perspective is the Einsteinian or general relativistic perspective. The Newtonian perspective is the older and rather obsolete perspective. We still use Newtonian physics a lot when it comes to, let's say, space travel. Uh, if you want to send people to the moon and bring them back, you can use Newtonian mechanics for it. You don't need to use general relativity. That's how accurate Newtonian mechanics actually is. But the correct picture, the correct perspective is the general relativistic perspective. So what will really happen is what I just described. Even though the sun has actually disappeared by magic, we won't know it for 8 minutes and 20 seconds. It's only then that we will suddenly realize the sun has disappeared. So that's how it goes, and we can't use these magical effects for travel faster than light or any such thing, because you cannot break the speed limit. You can't violate the universal speed limit, which is c, the speed of light. All right. Okay, Issue says, have you watched Netflix Three Body Problem? Is this a real phenomenon? So I have read the book a long time ago when it first came out. The first book, The Three Body Problem, by Cixin Liu, a Chinese science fiction writer. Great book, very very good book. And recently a Netflix thing came out, documentary, not documentary, series, right? I think I saw a couple of episodes of that. And so, what is the three body problem? Is the question. Is it a real phenomenon? So, the three body problem is a bound state problem. It's a Newtonian bound state problem. So, bound state problems can be solved in a variety of ways. You can use, if it's the Earth Moon system, for example, or the Earth Sun system, you can just use Newtonian mechanics to calculate the orbit and all that. calculate the size of the orbit, the periodicity of the orbit, and so on and so forth. We have Kepler's laws, which are part of Newtonian mechanics, celestial dynamics, and so on. You can compute orbits and trajectories and whatnot using the uh, Newtonian physics. You can also actually solve the Schrodinger equation for the Earth Sun system, or the Earth Moon system, using a gravitational potential. Okay, that is complicated. I'll not go into that. Sounds complicated. You don't know what a gravitational potential is, and so on. But you can actually you solve this bound state problem not using Newtonian mechanics, but using the quantum formulation, the Schrodinger equation. That also works, but it's a bound state problem. Earth Sun or Earth Moon. Now, instead of a two body problem, Earth Sun, let's say we try to solve a three body problem. Somewhere in space there are three gravitating objects. They are close to each other, which means they feel the pull of each other's gravity. So it's not a bound state of two objects, two gravitating objects. It's a bound state of three gravitating objects. That's the three body problem. Now, that is something that typically doesn't have a stable solution. There are a few stable solutions, but most solutions are unstable solutions, which means the bound state is unstable. It breaks up. It will evolve for a time, and then it will break up. It is unstable. So it is a bound. So it's not a bound state actually. Now there are a bunch of solutions that, and it's very difficult. It's a very chaotic system. It's very hard to find solutions from the Newtonian perspective. Now, if you want to see what some solutions look like, I could do that. Okay, so this is an image that represents a few stable solutions to the three body problem. As you can see, each of these images represents a three body system, and it has stable solutions, which means that the bound state remains stable. It doesn't break up. What does it mean for a bound state to break up? It means that one or more of these objects will fly off into space and not return together, not come back into the system. So these systems that you're seeing, these solutions are stable solutions, and they can persist indefinitely. And recently, I believe some physicists or mathematicians derived a whole bunch of more solutions, maybe 12,000 or so solutions to this three body problem. So overall, it's a chaotic and unstable system, and that's the premise behind the science fiction book and the series, the three body problem. So yes, is it a real phenomenon? Yeah, you take three bodies, three objects, gravitating objects of reasonably similar masses, you're gonna have a chaotic system, which typically will break up over time. So it's a real phenomenon. But whatever else is depicted in the story, in the science fiction story, the unfold of photon and all that, that is in the realm of science fiction for sure. Okay, so we don't know if a proton can be unfolded. The premise is that there are lots of hidden dimensions, multiple dimensions, string theory premise. Maybe 10 dimensions, maybe 11, maybe 26 dimensions, and maybe this alien civilization has the technology to unfold the dimensions and engineer the inside of a proton. So that sort of thing. And then there is some stretching of quantum mechanics in there, when they say that you can have a quantum entanglement in which there is transmission of information. That is not right. So that it's not how it works. Some of it is fiction, some of it is actual science. Okay, next question. Okay, Rohan Bidi says, is it true that achieving absolute zero temperature is impossible? And is there an upper limit on how hot an object can get? So, what is the upper limit of temperature? Is the question, right? So, first of all, the lowest temperature you can have is called absolute zero. Absolute zero is about minus 273 degrees Celsius, which is 0 Kelvin. Hmm? So, absolute zero is 0 Kelvin on the Kelvin scale, which is minus 273 point something degrees Celsius. and Fahrenheit it's something else. So that is what absolute zero is, and that is the theoretical lowest temperature that you can have. So theoretically, the lowest temperature can be minus 273 point something Celsius, which is 0 Kelvin. It's not 0 degrees Kelvin, it's 0 Kelvin. So at this temperature, absolute zero, the motion of all particles in a substance will cease, which means that the substance will have zero kinetic energy. Of course, there is something called zero point energy, which I will not go into. It's a quantum mechanical thing. But overall, all energy, all motion of molecules, vibration, whatever, rotations, etc., everything will cease. So the substance will have zero kinetic energy. Now, is this possible? In reality, in reality, the it is not possible to achieve absolute zero. And this is because of the third law of thermodynamics, which states that the temperature, as the temperature of a system approaches absolute zero, its entropy, or the measure of the disorder on the system, will approach a minimum value. Okay. And this law also implies that it's impossible to reach absolute zero in a finite number of steps. So you can reach absolute zero, but it will take you an infinite number of steps to get there. So that's why it's practically not possible. So in practice, if you have a system, let's say you have a box and you're refrigerating it, you're taking as much heat out as possible. So the system inside the box gets colder and colder. Okay. Now, as the system gets colder, it's going to get more and more difficult. It's going to get increasingly difficult to remove whatever heat is left, because there's already very little heat left, and you're going to have to do tremendous amount of work to extract that heat out and take it out. Okay. So there are various methods that are used for cooling. Uh, Refrigeration has your standard methods, then there is laser cooling and whatnot. So these methods can bring your substance or your thing, whatever it is, your gas or liquid or whatever it is, to very close to absolute zero. But you can never reach exactly absolute zero because of these limitations, thermodynamic constraints, quantum mechanical limitations, and all that. So achieving absolute zero is practically impossible. It's not going to happen. You will not be able to achieve absolute zero. Now, what's the upper limit on temperature? Is there an upper limit on how hot an object can get? Well, theoretically, unlike absolute zero, there is no known upper limit. No, there's no known fundamental upper limit to temperature. So you can make something as hot as you possibly can, eh, using practical means. So there is no fundamental upper theoretical limit on temperature. Uh, there is something called a Planck temperature. Okay, so the Planck temperature is approximately what, 10 raised to 32 Kelvin. 10 raised to, and when it comes to the highest temperatures we have achieved on Earth, I think when it comes to colliders like the Large Hadron Collider or whatever, you may have a temperature of maybe on the of the order of a billion Kelvin, 10 raised to 9 Kelvin. But the Planck temperature is roughly about 10 raised to 32 Kelvin. So that is a difference of a factor of 10 raised to 23, which is ridiculous, enormous. So the Planck temperature is, so that is derived from various fundamental physical constants. It represents the scale. The Planck temperature represents the scale at which the effects of quantum gravity are expected to become significant. Uh, and At the Planck temperature or above the Planck temperature, the current physical theories will break down. I mean, we don't have, uh, we believe it is the current physical theories like general relativity, quantum mechanics, or whatever else, they are insufficient to describe the behavior of matter and energy at the Planck temperature or above the Planck temperature. So we don't know how matter, energy, etc., will behave at that scale and above that scale. So it's not a limit, but it's where our understanding of physics breaks down. Okay, so that's what it is. So there is no established theoretical fundamental upper limit on the temperature that you can achieve, but the Planck temperature is a theoretical boundary beyond which our understanding of physics breaks down. It no longer applies. So that's what it is. So absolute zero, achieving absolute zero is impossible from a practical perspective. Achieving as hot a temperature as you can is not impossible theoretically or practically, but our understanding of physics breaks down at and beyond the Planck temperature. And obviously, when it comes to a practical perspective, the highest temperature we can achieve is of the order of 10 of a billion Kelvin, 10 raised to 9 Kelvin, which is way, 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 way below the Planck temperature. It's puny compared to the Planck temperature. So, yeah, that's the answer. Okay, feminist slayer says, are electromagnetic waves attached to space? And if so, does it mean that they don't have their own speed but rather travel with the speed of space, which would be the Hubble speed in the present time? Well, okay, interesting question. The Hubble speed is what, 60 something or 70 something units, right? Uh, Now, that's not the speed of light. We know that light travels at 300,000 meters per second. That's the speed of light, roughly. Okay, don't nitpick, don't be pedantic. It's roughly 300,000 meters per second. That's the speed of light in vacuum, and also in air, mostly almost the same. In water and other substances, in other media, the speed of light is less than that of the speed of light in vacuum and air, but you get it. So the real question you're asking is, are these electromagnetic waves attached to space? Which actually, what you're actually asking is, what are you asking? What you're asking is, do they need a medium to propagate? Is space the medium in which they propagate? It is. But here's the answer. Electromagnetic waves don't need a medium in which to propagate. So space is, you can think of it as a vacuum, and they travel through space. They're not attached to space, and it's not the expansion of space time that is making electromagnetic waves travel. Okay, it's not that. They travel within space. They travel through space. They're not attached to space or space time. So they can travel. They don't need a vacuum to travel. So they can travel through space. They can travel through air, the atmosphere of the Earth. They can travel through the atmosphere of Venus. They can travel through water, but in water it doesn't work. They don't travel. They don't propagate that well, which is why if you go below a certain depth under the oceans, it's complete darkness because they can no longer reach there. So each medium is different, and so on. So yeah, that's the answer. The electromagnetic waves are, they have their own speed, which is the speed of light. That's the fundamental cosmic speed limit. And an electromagnetic wave is made up of an electrical component and a magnetic component that oscillate at right angles at 90 degrees with each other, and that's how they propagate. So they're not attached to space. They don't need a medium for being able to travel, and they travel at different speeds in different media depending on the properties of the medium. All right. Arjun Sinha says, what are cosmic redshifts? What is a redshift? Have you heard of the Doppler effect? So redshift is about the application of the Doppler effect to light. So now let us go to, let me put an illustration of the Doppler effect on the screen, and then let me explain what redshift is. So Doppler effect. So here we have the Doppler effect with a sound source. Okay, let's say you have two cars. Let's say you have okay, with a train, right? We are all familiar with the Doppler effect with the train. So when you have a train coming towards you at a high speed, and the train blares its horn or siren, you're gonna hear a very high pitched sound as it's coming towards you. But the moment the train passes you, you're standing on the platform and the train is coming towards you, it's going to be very high pitched sound. The moment it passes you and it starts going away from you, the sound changes in frequency and it becomes a lower pitched sound. That is the Doppler effect. And the reason for that is because when the train is coming towards you, the sound waves are compressed. That's why they sound higher pitched, or they sound as if they have a higher frequency, because they do have a higher frequency from your perspective. And when the train passes you and it goes away from you, then the source of the sound is moving away. And that's why the sound waves are stretched out and they appear to have a lower frequency. So that's how the Doppler effect works with respect to sound. And the same thing happens with light. So when a light source, so light is an electromagnetic wave. And this wave is going to have a frequency or a wavelength. And when a light source is moving towards you, those light waves are going to get compressed, squashed, and they're going to have a higher frequency and a shorter wavelength, which means the light will be shifted towards the blue end of the spectrum. You know, Vibgyor, right? Violet, indigo, blue, yellow, orange, red. The seven elements of the spectrum. So when the light source is moving towards you, the light is going to be shifted towards the blue end of the spectrum. That's called blue shift. And when a light source is moving away from you, then the light waves are going to get stretched out, and the light is going to be shifted towards the red end of the spectrum, and that is redshift. So when you observe redshift in the cosmos, when you observe, and how do you know that something is redshifted? So there are certain characteristic lines in the spectrum. In spectroscopy, you know that that each element has certain transitions which produce characteristic lines in the spectrum. Wanna see what a spectrum looks like? Okay, let's look at the spectrograph. Spectrum. Let's see what a spectrum looks like. Spectral lines. So these are spectral lines. Okay, every gas, you have a star in which you have different elements. You have hydrogen, helium. There's gonna be other elements also. So they're gonna have various lines in the spectrum, and we can break down these lines into the element into their components using something called a spectrometer or a spectrograph. So you have various spectral lines and all that. So now we know that each spectral line has at which frequency it exists. So for example, if you burn sodium, it produces a very characteristic line on the spectrum, and we know what is the frequency of that. But when you observe that line in the spectrum of light that's coming from a galaxy, you're going to see that it's not at that frequency, it's at a different frequency. If it is shifted towards the red end of the spectrum, then that galaxy is red shifted. If it is shifted towards the blue end of the spectrum, it is blue shifted. So when you find that light is red shifted, it means the galaxy is moving away from you. And depending on how much it is red shifted, you can determine how fast it is moving away from you. And similarly for blue shift. So that is what a red shift is. That's what the blue shift is. How do we know galaxies are rotating? Because if you see the light coming from one end of the galaxy, it's going to be either red shifted or blue shifted. And the other end, if this part is red shifted, this part will be blue shifted. And if this is red shifted, this will be blue shifted. So you know that one end is moving away from you and one end is moving towards you. That's how we know that galaxies rotate. And then, yeah, that's how it goes. So that is what cosmic redshift is. That is what redshift overall is. Rohan says, why is gravity the weakest of the four fundamental forces of nature? So we know of four fundamental forces. The four that we know of. The weak electromagnetic force, the strong sorry, the weak nuclear force, the strong nuclear force, the electromagnetic force, and and gravity. These are the four forces that we are aware of. Okay, so now how do we know what are the strengths of these forces? That's a good question, and let me once again go to our friend Google, and there's a great website that you can check out. Okay, if you want to see basic physics, hyper physics. So hyperphysics is a great website, and let's look at coupling constants. Coupling constants for the fundamental forces, and we go there. Okay, let me embiggen this, bigify. Okay, so so every force has a coupling constant. I'll not go into what a coupling constant is because that will be a whole different explanation. But every force has a coupling constant. So the strong force has alpha s, the electromagnetic force is alpha, the weak force is a coupling constant, and gravity has a coupling constant. And see the strengths. So the coupling constant strength for the strong force is of the order of 1. It's dimensionless. It could actually be zero point 0.1 or something, but let's say it's 1. Then the strength of the coupling constant, the value of the coupling constant of the electromagnetic force is 1 upon 137. So that's about of the order of 10 raised to minus 2. The weak force, that its coupling constant has a value of 10 raised to minus 6. So that's 4 times weaker than the electromagnetic force, roughly. And then gravity has its coupling constant has a value of 10 raised to minus 39, which is ridiculous. It's about 10 raised to it's about 10 raised to 33 times weaker than the weak force. Incredibly weak. That's how incredibly weak gravity is. Okay, so gravity is the weakest of forces by a massive margin, incredible margin. The weak force is the other weakest force. Neutrinos interact only via the weak interaction, and the sun produces trillions trillions of solar neutrinos per second. And right now, trillions of solar neutrinos are passing through my body. Right now, trillions of solar neutrinos are passing through my body every second. And none of them is interacting with me. No interaction. I don't even know that this is happening. I don't sense anything, but it's there. So the weak force is so weak that the enormous majority of these neutrinos don't interact with regular matter, electromagnetic matter. But the gravitational force is about 10 raised to 33 times weaker than the weak force. Imagine how weak it is. So that gives you an illustration of the relative strengths and weaknesses of the forces. And the gravitational force is the weakest by far. Now, why is it so? That's the question. We don't know. There are theories, there are hypotheses as to why it is so, but we don't really know. And one of the straightforward answers I can give you is that string theory gives you uh, gives you an explanation of why it is so, but we have no proof of that. String theory, M theory, brain world theory, whatever you want to call it. So in M theory, uh, the universe was born from the collision of what's called two brains. A brain is a three-dimensional object which lives inside a higher dimensional bulk. So if you have a sheet of paper, it's kind of a two-dimensional object. It has length and breadth and no thickness, almost. So a sheet of paper is a two-dimensional object that resides in a three-dimensional world, correct? Similarly, the universe, it it is kind of, you can say, a brain, a three-dimensional object that resides in a, let's say, 10-dimensional bulk, string theory bulk. And the universe was formed, the Big Bang was the result of the collision of two brains. That's how it is in brain world theory, in M theory. So in string theory, superstring theory, you may have 10 or 11 dimensions. Now, where are these dimensions? Why don't we see them? We can see length, breadth, and height, right? Every object has a certain length, certain breadth, and certain height. And time can be the fourth dimension. So we are aware of 4 dimensions. We can perceive and sense and observe 4 dimensions. But what are these 10 dimensions that string theory talks about, or 11 dimensions, or 26 dimensions? What are these dimensions? So according to string theory, these dimensions are ultra compactified. They are very small, very tiny dimensions. You can't see them, but they exist. So according to string theory, superstring theory, the three forces, the strong force, the weak force, and the electromagnetic force, they are their effects are felt only in the 3 dimensions that we observe. They propagate only in these 3 dimensions. But gravity propagates in all dimensions. So much of the strength of gravity leaks out in these unseen dimensions, and that's why it is so weak in the three dimensions that we perceive. That is the theory. Do we have any evidence of that? None. Okay. Have we ever observed extra dimensions? No. And if extra dimensions and all that existed, then the LHC would probably, the Large Hadron Collider would probably have produced micro black holes. Okay. So before this thing was turned on, the Large Hadron Collider in the 2000s, before 2010, there were lots of papers that were published that predicted that the Large Hadron Collider would produce about one micro black hole per second or something like that. And that had something to do with extra dimensions and all that, and it never happened. We know it never happened. And there was a campaign, a movement to stop the LHC because it would produce possibly micro black holes, and these black holes would eat the Earth up. So we would be destroyed. So there was this campaign to stop the Large Hadron Collider. Anyway, so the only theory that kind of explains why gravity is so weak is superstring theory, but there is no evidence that proves the correctness or validity of string theory. But it makes sense from that perspective. So that's perhaps why gravity is the weakest of the forces. Let's take a couple more questions. What was there before the Big Bang? Why did the Big Bang occur at the exact time it happened? So we don't know. We have no data from before the Big Bang. Whatever data we have, whatever observational evidence we have. See, whatever theories you make have to be in synchronicity with the observational data, empirical evidence, and the laws of physics. So we know the laws of physics. At the largest scales, the universe is governed by general relativity. We know that. And then we have all this data of all this observational evidence of stars, galaxies, the redshifted galaxies. They're all moving away from us, and the expansion of the universe is accelerating. We have cosmic microwave background radiation. All of this data, all of this evidence is there. So that is what helped us formulate what is called Big Bang cosmology, the lambda CDM, lambda cold dark matter model of the universe. Okay. But this data that we have, it says nothing whatsoever of what could have existed before the birth of the universe, the Big Bang. So, from a data perspective, from a scientific perspective, we have zero evidence of anything that came before the Big Bang. So we don't know what was before the Big Bang. But there are theories, like I said, in M theory, in superstring theory, etc. The Big Bang itself was the result of the collision between two brains, three-dimensional brains that exist in a higher dimensional bulk, and the collision of these two brains and the energy it released, or the energy of the collision, was what created the Big Bang, and the Big Bang is the creation of the universe. So maybe it's that. But we have zero evidence for that. Mathematically, it makes sense and all that, but evidence is key in science. A theory, if it is not falsifiable, is not a scientific theory. It's philosophy or religion. So from that perspective, string theory is all philosophy. It's not science. Well, okay. M. Thanos says, we know energy is created from mass. No, we don't know that. We don't know that. Okay. We don't know that energy is created from mass. Now, can this reaction be reversed? I read it can be, but requires enormous amounts of energy, like Big Bang, to happen. So can mass be converted into energy? Can energy be converted into mass? That sort of thing. So can mass be converted into energy is essentially what he is asking. Yes, it can. Mass can be converted into pure energy. I'll tell you how. Let's say you have a proton. Let's say you have a hydrogen atom. What's a hydrogen atom? It's a proton as in the nucleus, and it has an electron that goes around the proton. So that's what a hydrogen atom is: an electron in orbit, in a shell orbit around a proton, which is the nucleus. So that is, let's say, the matter, the mass that you have, one hydrogen atom. Now, how do you convert it into pure energy? It's very simple. You bring in an atom of anti-hydrogen, which has an anti-proton at the center and a positron in a shell orbit around the anti-proton. So that's hydrogen, one atom of hydrogen, one atom of anti-hydrogen. That's matter, antimatter. You bring them together, they're gonna give off, they're gonna annihilate and give off pure energy, generally in the form of photons. Yeah, so it can happen. So matter can be converted into pure energy by annihilating it with antimatter. Right? Okay. A.D. Guru Prasad, he asks a very interesting question. And the question is about entropy. Please explain entropy. Entropy. I've had so many discussions and arguments about entropy in the past. Anyway, what is entropy? Entropy is a fundamental concept in physics, but also in chemistry. Okay. And it essentially is related to the degree of disorder or the degree of randomness in a physical system. What's a physical system? Let's say you have gas in a box. That's a physical system. How much disorder, how much randomness do you have in this gas in the box? That's that measure of disorder or randomness is called entropy. So entropy, it plays a crucial, critical role in the second law of thermodynamics, and it has important implications in various processes, chemical reactions, and so on and so forth. So in physics, we have a branch of physics called thermodynamics, in which entropy is a measure of the number of. See, you have a system, you have a gas in a box. What is the number of specific ways in which your gas, this thermodynamic system, can be arranged without changing the overall state of the system? So this is the measure of the randomness of the system, the measure of disorder of the system. So the ways in which you can arrange a cold gas, it's different from the number of ways in which you can arrange a hotter gas, and so on and so forth, ice versus water, and so on. So the second law of thermodynamics, it says that the total entropy of an isolated system can never decrease over time. And this implies that natural processes move from states of move they tend to move, they want to move towards a state of maximum entropy or thermodynamic equilibrium. And then you bring in statistical mechanics and all that. You have the Boltzmann entropy formula. S is equal to kb ln omega, where kb is the Boltzmann constant and omega is the number of microstates. S is entropy, and so on, and so on and so forth. So entropy is a statistical property of a system. It's the measure of the disorder of a system. An intrinsic particle like a proton or a neutron or a bound state can never have entropy. It's only a combination, it's only a bunch of particles, a system made of lots of particles, that can have entropy. And there is entropy has it has a meaning in chemistry as well. Entropy, when you have a chemical reaction in chemistry, the entropy of the system changes, and the change in entropy is it tells you, it is it tells you how spontaneously the reaction happens. So the spontaneity of a reaction, it is dependent on the kind of entropy change the system undergoes in a chemical reaction. And there is something called the Gibbs free energy equation, and that tells you how it happens. The positive or negative change in entropy will determine the spontaneity of the reaction, and so on and so forth. So entropy, it is, you can factor in molecular motion, you can factor in lots of other things, but overall it's the measure of the disorder of a system. In a system, you have lots of components, typically gas molecules, or you have water, or you have a liquid. So you have molecules in various configurations, and the amount of disorder in a system, that is the measure of that, is the entropy. So for example, if you take the system, the human brain is a highly ordered system, so its entropy is going to be incredibly low. And probably the lowest entropy system in the universe may be the human brain, because it's so orderly, so there's very little disorder, and so on. So all of that is entropy. Entropy is it's a thermodynamic property, it's a statistical property of a system. And please remember that intrinsic particles do not carry entropy, they don't have entropy. Okay, we'll take one last question before we go into the live chat. So, Geopolitical Dubey says, uh, what or who makes the perception? What makes the perception that scientists cannot be dharmic or religious, as he or she sees everything scientifically and dharma is not science? Okay, so let's be clear. There is a difference between science and philosophy, science and spirituality, science and religion. Now, religion and dharma are different. The Indian system, dharmic system, is different from the Abrahamic systems, which are religions. Dharmic system is different, and so on. But when it comes to science versus, let's say, philosophy, philosophy and spirituality can deal with non-physical objects. When we talk about the concept of the soul is not something you can measure. It's not something you can observe. Soul is non-observable. It's non-measurable. It doesn't have a weight. It doesn't have mass. It doesn't occupy volume, as far as we know. It's a non-physical object. So when we talk about non-physical objects, that is beyond the realm of science, right? When you are a scientist, you are absolutely disciplined that you only deal with physical objects, physical phenomena, and observable quantities. That is science. When we talk about philosophy and religion and dharma, when we talk about the soul and we talk about ethics and morality, these are not physical things. So you cannot bring science into that, or you cannot take that and try to apply science to that, and you cannot make science subject to whatever laws may or may not exist related to these non-physical objects. That's the difference. That's what differentiates science from philosophy and religion. Now, can a scientist be religious? Is it wrong for a scientist to be religious? Let me give you some examples. Have there been scientists who have been religious in history? Have you heard of Srinivas Ramanujan, one of the greatest mathematicians in known history? Mathematician. Well, he was deeply, deeply, profoundly religious. He said that every mathematical equation is something to do with God, and he used to see dreams of his goddess, his family goddess, and she used to give him equations, and he used to wake up and write those equations, and they would invariably be correct. So he was religious, deeply religious. That's one example. Uh, George Sudarshan, ECG Sudarshan, one of the greatest theoretical physicists of the 20th century. He should have won 3 Nobel Prizes. He was born into a Christian family in Kerala or South India somewhere, the southern India, but he was not a practicing Christian, he was a practicing Hindu. And maybe that contributed to him not winning a single Nobel Prize. He should have won 3 Nobel Prizes. That's how great and that's how brilliant George Sudarshan was. Do you want to see what it looks like? Let me put him on the screen. One of the greatest physicists that we can in our history. Let me put Google on the screen. So this is a scientist who was religious. Okay, one of the greats, one of the genuine greats. He was religious. He believed in God. Who else? Who else can we think of? Scientists who believed in God. Georges Lemaitre. Who was Georges Lemaitre? Let me tell you. Let's Wikipedia him. As always, Wikipedia is not a reliable source of information, but just for the sake of convenience, we'll put Wikipedia on the screen. So this guy, Georges Lemaitre, was a theoretical physicist. He proposed the Big Bang Theory. That's how significant he is. He proposed the Big Bang Theory. And he also derived what is now called Hubble's law, and so on. And who was this guy? He was a Catholic priest, and he was a theoretical physicist. Okay, let's take a look at something about him, work, blah blah blah, etc. etc. What do we have? Uh, let's go to this. Let's go to this archive paper about him. Editorial note to the beginning of the world from the point of view of quantum theory. So this is about a paper that Lemaitre wrote. And what does he write here? Let's see. This is something he had crossed out. He says, I think that everyone who believes in a supreme being supporting every being and every acting believes also that God is essentially hidden and may be glad to see how present physics provides a wheel hiding the creation. So, this is a guy who's a Catholic priest. He believes in God, and he is the person who proposed the Big Bang Theory, one of the greatest physicists, okay, theoretical physicists. And men, the predictions, his predictions were all borne out. They all came out to be true. Big Bang Theory, cosmic microwave background radiation, and much more. And he believed in God. So this is a Catholic guy or Catholic priest. Similarly, why can't you be a dharmic person and still be a physicist or a scientist? Of course you can. George the Sudarshan, he was a dharmic guy, dharmic man, one of the great geniuses of the 20th century. So when you do physics, when you do science, you do it through the scientific method. You don't bring in religion in there, otherwise you're going to end up with nonsense. And the scientific method emerged out of India. Now there are people who will say that you should. Okay, I'll not go into that unnecessary controversy, but that's the deal. So you can be a physicist while also being religious, because as a physicist, especially if you are at the cutting edge of physics, at the bleeding edge of physics, between the known and the unknown, the possible and the impossible, that's typically theoretical physics. Then you know that more than 95% of the universe is unknown to us. So when there is such when there are such enormous unknowns, it makes sense to have a to to consider seriously the possibility that there could be a divinity out there. So I would say most physicists, the more brilliant they are, the more agnostic they are, and some of them actually are believers in God. So there is, so it's some physicists, some scientists will say that it is wrong for a scientist to believe in God. I think those people are idiots, to put it very crudely. But yeah, okay, I think we're done with the questions from the comments. Now let's take some questions from the live chat. Now please ask me questions about science and physics. When it comes to geopolitics and other things, we'll take that day after tomorrow, not tomorrow. So in case you came in later, if you came in late, I am supposed to have a live stream tomorrow about geopolitics, history, and current affairs. I am postponing it to day after tomorrow because I have to be in Delhi tomorrow. I'm attending the inauguration and swearing in of Prime Minister Modi. So I cannot refuse that. I've been invited very graciously, so I have accepted that. So that live stream will happen on Monday 9 p.m. All right. So let's take some questions from the live chat. No questions about history, please. You can ask me those questions in the history live stream, history geopolitics. Nishant says, how do space telescopes like the Hubble Space Telescope, the James Webb Space Telescope create images? Are they accurate? A telescope usually has lenses, and you have to understand optics. So it's usually lenses and mirrors, or lenses or mirrors, and you can have prisms as well. There are different kinds of telescopes. Some are reflective, just like your cameras. I don't know, where's my camera? I've got a bunch of cameras. So you have something called an SLR camera or a DSLR, digital single lens reflector. So when you have a lens, a camera has a lens, right? Light comes through the lens. It's focused on an element which is a reflective element, and that it's a mirror which reflects the light onto the digital processor, and that's how the image is formed. Similarly, when it comes to Hubble or James Webb, I think when it comes to Hubble, there's a gigantic primary lens, and I don't remember what happens inside. Is there a reflector? Is there a prism? Is it another lens? But there are optical elements. In the case of the James Webb Space Telescope, okay, let's take a look at what it looks like. Let's put that on the screen. JWST, James Webb Space Telescope. So this is what it looks like. So you can see it's got a bunch. It's a compound mirror, and these are hexagonal mirrors all put together. And there is, and that light, whichever is collected on the mirror, is reflected into this smaller element, which will then process that. So let us say schematic. Schematic diagram. Do we have it? So yeah, if you look at this, it will tell you what are the components and how it actually works. So you have the primary mirror, 18 hexagonal segments made up of beryllium and coated with gold. There's a secondary mirror which gathers the reflected light, and then it gives that light to the primary scientific equipments, and these equipments, they all process the light and give you the scientific data, and so on and so forth. So that's how it works. So different telescopes work in different ways. You have Earth-based telescopes, you have space-based telescopes like Hubble, then you have the infrared telescope, which is James Webb. So the James Webb Space Telescope, so the Hubble Space Telescope, it primarily gathers light and data in the visible part of the spectrum. Whatever we see with our eyes is the visible range of the spectrum, and that's mostly the light spectrum in which Hubble gathers light and data. A little bit of infrared as well. When it comes to JWST, James Webb Space Telescope, it is designed to operate in the infrared range of the spectrum, because we want to be able to see the oldest light in the universe. And the oldest light in the universe comes from very, very far away, which is why it is highly stretched out. It is redshifted, and it is no longer visible to our eyes. It is so redshifted. So it is infrared light. So that's why the James Webb Telescope operates in the infrared uh, range of the spectrum, and that's why we've had to put it in orbit around the L2 Lagrange point in the shadow of the Earth. So that is very cool, and it is not impacted by light from the sun, and so on and so forth. So yeah, that's how it operates. To understand really how it operates, you have to see the schematic diagram and understand optics and understand various effects, and that's how it's done. And is it accurate? It's tremendously accurate. Of course it is. Otherwise, why would you spend so much money sending this instrument so far away and all that? Yeah. So it is indeed very much accurate. Okay. Okay, Zeus says, we have heard the famous sentence, either we are alone in the universe or we are not. Both are equally terrifying. My question is, what if we are the alone, the only civilization in the universe? Well, that's terrifying. Which means that if we mess up and we somehow extinguish ourselves, then there's no intelligent life left in the universe, right? I mean, we are always in the brink of disaster since the 20th century, when we discovered radioactivity in nuclear weapons, when we developed nuclear weapons. So today there are more than 10,000 or more than 11,000 nuclear warheads on the planet. And one slight miscalculation can set off nuclear war. If that happens, it's almost guaranteed to extinguish our species. And if we are the only civilization, intelligent civilization, or only place in the universe where there is life, then that is frightening, which means that human stupidity can end all life in the universe, right? So yeah, so the question, the answer, we don't know. Like you said, there are two possibilities: either we are alone or we are not. If we are alone, then we have such an incredible responsibility to continue life in the universe and intelligent life in the universe, which is us. And if we are not alone, well, that itself, that too can be really scary, which means there probably are other life forms elsewhere in the universe, which means that some of them could be more intelligent than us, which is dangerous, which is very dangerous, because yeah, that could be a threat. So yeah. uh Arijit says, can we input consciousness in an AI? We can't. First of all, we don't know what a consciousness is. We don't have a definition of consciousness. And to input something into an AI, we need to have it somewhere. Now, where is consciousness? I know there's a consciousness here. I know each person I see has consciousness and intelligence. I know cats, dogs, etc. have consciousness, horses. Every life form has some degree of consciousness. But what is consciousness? How do I physically localize it? How do I transfer it from one place to another? I don't know. So we don't have the means to do that. We don't even have any understanding of what consciousness is. We don't have a definition of consciousness. So as of today, we cannot do it. Do not ask me questions about history today, my dear friends. We'll take it in the history live stream, history geopolitics live stream. All right. Um, okay, Ritik says, do we need different types of physics to reach Alpha Centauri? It depends on how quickly you want to reach there. Let's say you want to reach Alpha Centauri in 100 years. So, how far is Alpha Centauri or Proxima Centauri from here? It's 4 point something light years away, which means if I shine a laser beam at that star system, it's going to take 4 point something, less than 5 years to reach there. But if you want to travel in a standard rocket, let's say the SpaceX Starship to Alpha Centauri, it's going to take you more than 100,000 years to reach there. More than 100,000 years at that speed. So you will reach there, but you will reach there in 100,000 years. Who wants to take that long? It's going to be God knows how many human generations. If it's 4 generations in a century, okay, and 10 centuries is 1,000 years, so that's 40 generations. 10,000 is 400. So 4,000 generations will go by roughly for 100,000 years. So that's ridiculous. So let's say you want to reach in 50 years. How do you do that? Do you need different types of physics, different kinds of physics? No. Physics will remain the same, but you will need different technology. You'll probably need to accelerate your vehicle, your spacecraft, to a certain to relativistic speeds, which means speeds that are comparable to the speed of light. Let's say 0.1 c, 0.2 c, where c is the speed of light. To do that, you will need to use different technology, not the chemical rocket technology that we have today. You would probably need to use light sail technology. And there is a project underway which could become operational in a decade or two, which is called Breakthrough Starshot, if I'm not mistaken. So they plan to make these solar sail equipped micro spacecraft, which will be accelerated to relativistic speeds towards Alpha Centauri, Proxima Centauri, using radiation pressure. So radiation and light itself can exert pressure on and if you have a large enough object like a light sail which is extremely thin, you can use sunlight itself or any other light to accelerate that spacecraft. So you use this micro spacecraft with light sails and you shine laser beams on that. It's going to accelerate that to relativistic velocities, and then those micro spacecraft can reach Proxima Centauri in 20-30 years. That is feasible with today's technology. Almost there. We're almost there. We would need gigawatt lasers, which we will shine from the surface of the Earth onto the spacecraft. So within a decade or two, we may be there. We may have the technology. So you need new technology, not new physics, to reach Alpha Centauri in a reasonable time frame. So we will soon be in a position to send robotic spacecraft to Alpha Centauri in a time frame of about 30 or so years. So the journey will take about 30 or so years. Okay. But sending humans will take longer because we will need a much larger light sail. And you will need a spacecraft that can sustain humans, keep them alive for, let's say, 30 years on a one-way trip, and then 30 years on a trip back, if you can do that. So that's 60 or so years, and so on. So we are still a little bit way off from being able to do that. First of all, we want to send humans to the moon and then to Mars, and then we can think of other things. So yeah, you need new technology, not new physics. Okay, let's take a couple more questions. Divyata Shukla says, are we in a simulation or are we a 3D being created by higher dimensional beings? So once again, we don't have answers to these questions, because to answer these questions satisfactorily, one way or the other, we need data. We need empirical evidence that says, oh yes, this set of data points tells us that we may be in a simulation. So how do we know that we are in a simulation? We have to perhaps devise experiments that would indicate that there's a simulation. What's a simulation? It's like a computer program. We play these games, right? PlayStation games. Today we have PS4, we have Xbox, whatever. And 20 years ago, I mean, I had a PlayStation 2. I bought it a decade or 2 decades ago when it was brand new. It had just come out. I had a PS2. And the resolution of the games wasn't that great. But today, the PS4 or whatever it is these days, the resolution is much higher. So similarly, the universe we live in has a certain resolution, and maybe with sufficient RAM and sufficient whatever else, computing power, you can create a universe with this amount of resolution in detail. And maybe it's the most parsimonious hypothesis that this is a simulation, actually, right? So we could be in a simulation. It's actually possible. It may even be likely. Some people say it's quite likely, like Elon Musk and so on. But is it this way or that way? Is it a simulation, or are we three-dimensional beings created by higher dimensional beings? We don't know. To know, we would need evidence. We would need data. That's how science works, and we don't have it thus far. So maybe we can perhaps in the future devise experiments that allow us to find some data that could either prove this theory or falsify it. Chirag says, why are big tech companies putting biases in their AI and chatbots? Why can't they make their AI unbiased? So, what is algorithmic? So, this is a phenomenon called algorithmic bias. And when we have machine learning algorithms and all, they're whatever they're going to output to you depends on what they've been trained on, the data set they've been trained on. So generally when you have an AI chatbot like chat gpt 3.5 or whatever version is out there today, and other chatbots like Claude or Grok or whatever, they are trained. These are large language learning models trained on tremendous amounts of data, information, text and images and whatnot. Now, whatever data you use to train this AI system, the AI system is going to talk like that. And that data, all that information, that's going to be the sample size. And if that information is biased in some way or the other, then the AI will also be biased. Let's say you feed the AI trillion. Uh, let's say you input 1 petabyte of English language text into it. So English language text will have a Eurocentric bias when it comes to historiography and all that, and so on. So it's gonna incorporate and imbibe those biases. Let's say me, let's say I become a billionaire and I create my own language learning model and I input it only Sanskrit text. Then it's gonna be a Sanskrit speaking AI, and it's gonna have an Indo-centric bias and so on. So that is algorithmic bias. Can you make your AI unbiased? It's very hard to make it unbiased, and sometimes you deliberately introduce biases into your AI. So if you want to, well, if you want to have your AI conform to certain ideological standards, then you can program those biases into it, either by feeding it text and data which is already biased towards that ideology, or you can program some constraints on top of whatever it's already been trained on. So you either do it unknowingly or you do it knowingly. So yeah, so every organization, every government, every culture, every nation, every civilization has biases and has agendas, and that's what is naturally gonna be seen in AI systems. So you do it typically to further an agenda, a national agenda, a geopolitical agenda, an ideological agenda, a religious agenda, a racial agenda, whatever it is. That's just how it goes. Okay, let's say, one last question. Tony Paul says, why can't we know what's out there beyond the event horizon of a black hole? The event horizon is the boundary between me and the black hole, at which once a light ray crosses that, a photon crosses that, even that light cannot come out of the black hole. So the boundary is the event horizon. So why do we not know what's beyond that? So if I'm an observer and I have a black hole sitting in my lab and I want to know what's beyond the event horizon, what can I do? I can try and shine a light beam at it or some other kind of beam, but all of that, whatever I'm shining at the black hole, is going to be absorbed. It will never come back. So it's going to remain dark. That's why I cannot see what's inside. From an observer's perspective, that's the problem I face. From a theoretical perspective, general relativity tells you that beyond the event horizon, inside a black hole, at the center of a black hole, there is what's called a singularity. A singularity is a region of space time where the curvature of space time becomes infinite. The density of mass and density of energy also becomes infinite. Now, from a mathematical perspective, an infinity is a division by zero, which is unphysical, which means it actually is telling you that there is something wrong with your equations. Your equations are blowing up, they're breaking down at that point, which tells us that we need to improve the theory of relativity, the Einstein field equations, and make them compatible with the quantum world. Because singularity is it's an ultra microscopic region of space essentially. So that's what it is. So our theory doesn't tell us what's inside there. It breaks down and gives us an infinity, a singularity. And from an observational perspective, because the event horizon is the point of no return, we can't shine a beam of light in there and see what's inside. We simply can't. That light will be absorbed, it won't come back. So that's why we cannot know what's beyond the event horizon of a black hole. Firstly, we don't have a black hole in a lab. Secondly, even if we had it, we could not shine a beam of light on it and see what's inside. And thirdly, most importantly, our theory is imperfect. We need a better theory. We need to improve general relativity. We need to formulate a quantum theory of gravity, which incorporates quantum effects with which reconciles quantum mechanics with general relativity. Then we may know what's inside a black hole. Until we do that, we don't know what's inside a black hole. Okay, I think we have crossed 2 hours. Okay, let's take one last question. Durvesh says, what's the grandfather paradox? It's something to do with time travel. Let's say time travel is possible. According to certain solutions of general relativity, wormhole solutions, etc., time travel could be possible. So here's the paradox of time travel. Let's say there is a guy who's 20 years old, okay, and he is gifted a time machine for his 20th birthday. So this guy is something wrong with him, okay? He's violent and all that. So he takes the time machine, he travels back, let's say 50 years or 70 or whatever years, and he goes back in time and he meets his grandfather when his grandfather is a baby, 6 months old. And for some reason, he kills his grandfather. And then he comes back to the present day. Now, so this guy goes back in time and kills his grandfather when the grandfather is 6 months old, which means that the grandfather is dead at 6 months, and the guy who killed the grandfather, his father could never have been born. So how does he exist? Because his grandfather died 60 years ago, and the father was never born. So how does that guy exist? The guy who killed the grandfather. So that's the paradox of time travel. It causes a breakdown of causality. Causality, the causal structure of the universe, cause and effect. There is no effect without a cause, without an underlying cause. But by traveling back in time, you can create situations where causality breaks down. And that is the grandfather paradox. All right. Okay. I think we are done for today. We have crossed 2 hours again. So thank you so much for all your questions. I really appreciate that. And I will see you in the next live stream, which will happen on Monday, not tomorrow, because I have to be in Delhi for the Prime Minister swearing in tomorrow. So I will see you in the next live stream on Monday or in any of the live streams next week. So thank you so much for all your questions. Thank you for your viewership. I really appreciate that. And I will see you very soon in the next live stream. Take care of yourselves. And as always, don't forget to keep raising your standards. Thank you. Bye.